Hello, welcome to this webinar on formal validation of constant data for critical systems. We are going to see how formal methods can be applied practically to this activity in conformance with safety standards. Today, I'm with Erwan Motin, Business Unit Manager and in charge of development and validation of safety software. Hello, Erwan.
Hello, everyone.
And with Vincent Germain, System Engineer, expert in safety software validation and in the development of associated tools. Hello, Vincent.
Hey, everyone.
This webinar is aimed at railways operators, signaling system suppliers, and certification bodies. However, it's not restricted to railway transport, as it covers all application domains dealing with critical constant data. This webinar does not require any prior knowledge or skill to be followed. So this webinar contains a presentation and two demonstrations on real-life topics lasting approximately 30 minutes. The slides can be downloaded in the handout section on the right of your screen. And the video of the presentation, as usual, will be available on CLIS's YouTube channel in the coming days. During the webinar, you can ask questions in the chat room, again on the right, and we will answer your question at the end of the presentation. So let me switch to the presentation slides. Erwan and Vincent, the floor is yours.
Thank you, Thierry. Okay, so let's begin this webinar by talking about the formal data validation activity. You all know that in the rail industry, as well as in other sectors, projects are carried out in a generic way, and industrial build the generic product first. In a second phase, they will set the parameters for the need of the projects. We refer here to engineering rules, deployment rules, and every constraint exported by the project. That means that we now need to validate all these parameters. Historically, this validation was done manually. So you print your track plan, you take your piece of paper, you take your pen, and you try to check every single object. And you better know the properties like the back on your hand to do so. As you can see, manual validation is a repetitive task. Volumes can be very large. Sometimes you have to deal with complexity. So it's prone to human error. Let's take an example. This one is extracted from the report of the BEATT, the Land Transport Accident Investigation Bureau in France, which is available on the internet. This report, dated on July 2021, talks about another speed incident involving a high-speed train at La Milles in 2019. This train had to take another route due to some incident on the main track. And during this detour, it went through a point at over 170 kilometers per hour, whereas 100 kilometers per hour was the theoretical maximum speed to take the switch on that direction. So the report indicates under what circumstances it happened and why. As always, it's a combination of multiple errors. There was an error in the manual setting of the parameter, there was an error in the double manual verification, and an error on the test coverage. Problems appear when you want to validate a lot of things manually because we are not machines. And the conclusion of this report is that manual validation techniques are no longer adapted to the industrial project of this size. And as a result, formal data validation is a natural evolution of this process to increase confidence, to increase safety, and above all, to have exhaustive coverage of what we want to verify. Now let's talk about what are these verification rules and where do they come from. First of all, there's a CLIS webinar on this topic. You may have been able to follow it on the formal proof of system that explain how a critical system export constraints and property that the data must verify. If you have not, there will be another webinar by the end of the year. We'll keep you posted. So these properties that we want to verify, it can be topology constraints, it can be constraints related to an equipment on the track. For example, in the case of your accident, the maximum speed limit, depending on if you are in the normal or the reverse direction to cross the point. And at the end, there are hundreds of properties that we want to check on this data. And how are we going to do? Well, at ClearC, we use a certified tool, especially designed to do so. We are talking here about the ClearC data solver, which is T2 certified by an independent safety assessor for SEAL 4 use, which is the maximal level of the safety in the CENELEC 50128 standard. And with this tool, we will perform an automatic data validation. So automatic data validation is based on the same verification principle than manual verification, except that instead of checking it manually, the tool will do it. So what we need to do is to translate those verification principles into formal language. To do so, the first step is to remove ambiguities. Usually, we create something like a clearer specification. And this process is a huge advantage for you because we now have a document that lists every property and every rule you have to verify instead of having them in the brain of your experts. Last, we produce the formal rules by using formal methods, meaning that we translate those principles into rigorous mathematical language. We also describe to the tool how to access the data, and then we launch the verification campaign on the selected rules. The tool will produce an exhaustive report in English. So it's technical language here in this report. Understand that the aim isn't to know mathematics to be able to use the tool. The aim is to give the tool to your verification team that knows the data and the railway principle. The advantage of the tools are the following. First, the speed, the fact that it's automatic and you can repeat it over and over again. The reuse, when you want to verify other lines or other projects, well, you are going to apply the same properties. The cost, the return of investment on this tool is really good, even with only one project. The other advantage is that it's exhaustive, it's safe, it's user-friendly because it displays clear results on what needs to be corrected or what needs to be analyzed. So once again, no notion of formal method is required here to use the tool. We also can do some continuous integration. And last, it can be integrated into track plan editors, for instance, to display errors directly on the track in their context or something like that. So it's been 20 years now that ClearC has been doing formal data validation. We started with the ERTMS, who initiated the movement in 2003. And with them, we designed the first formal data validation tool. After that, other industrials started to use this powerful technique. I'm thinking in particular of Alstom in 2012, which was the first project to validate the data on an industrial scale using formal data validation techniques. More recently, we started projects either on urban and mainline projects with major actors in Europe and North America. I know that recently, ERTMS and SNCF are adding a requirement on their tenders to specifically request formal data validation to their suppliers. Now I'm going to hand over to Vincent, who will explain in detail how to validate the data and show you concrete examples.
Thank you. So now, if we take a real-life example, so what is our process? So first, we will need to discuss with your experts to define the real need for the validation. So what are the properties that the data must respect? From these properties, we will have a formalization of these properties in a mathematical language. And then with that formalization, we can produce the validation rules. The rules will be run by the tool, the ClearC data solver, to tag the data as OK, compliant, or not OK, non-compliant, with a message in French or English saying why it is non-compliant. So, this message will be in the validation report. So if we take a first example on a CBTC, so for this one, we'll use a quite complex rule. So we have transponders all over the tracks, and we want to avoid a train to read a transponder that is not on this track. And this can happen when you cross a switch. So if you are, for example, on a normal track and you have a transponder on a reverse track after the switch, if it is too close to the point, then your train could read this transponder and then have a mismatch on the location, which could lead to a dramatic event. So if we take a look more closer to this example, our beacon or transponder can be put somewhere in our track, and it has to respect a distance that can be computed depending on different parameters, but we need to define them to formalize them. So what are the properties here? We will need to take a look at the maximum range that can be guaranteed for the beacon, so where it can be read by the train, and also the radius for the curve that is taken by after the switch on the other track. And with that, we can compute the distance between the beacon and the point that has to be respected, and compare it to the actual distance where all the beacons are installed. So let's take a look at the example with a demonstration with the tool. So we have the ClearC data solver here. We started it in English. You can select the French language. We are in the CBTC panel, and we have this rule for the crosstalk that will be run. In the blue panel, we can select the data that we will use for this example, and in the orange panel, we can take the file that describes the format of the data so that the tool can access it. Then the tool asks where to put the report, and it runs the rules. The rule first is in progress, the execution, and then it will tell you that it is completed. So here it is not okay. You have some metric on the top left, and on the top right, you have some general information about the import status and generation of the report. So if we take a look at the data, at the report, sorry, so we have three different formats: CSV, XML, or Excel. Excel is the most visual, so let's take a look at it. First, the spreadsheet is traceability, so all the files that are needed or imported by the tool are here, and you have a checksum so that you can verify if they are modified after another execution. The second panel was for import status, and this one gives you information about the rules. So here you have the details for this rule, so the specific message saying why it is not okay. So you have a distance that is too small comparing to the expected one. Another way to see it is in the colorized input. So those are the inputs for the rule. In yellow, you have the data that are imported. And you can see that for the beacons, it is green for the position that are okay and red when it's not okay. And you have the same message that we had in the report before. So that way you can check the coverage that every beacon has been validated. Okay. So now that we have seen this CBT case, we can take a look at another case, which is for ETCS, for mainline validation. And for this demonstration, we can first add an additional step. So when we have data, usually it is digital information, but it can be also in a different format, which is not something that can be imported in the tool directly. For example, an image or a PDF with the scheme plan. And in that case, it's quite complicated to validate the data. And we will show you another way to avoid this issue and to validate it anyway. So here, if we take another example, we can have a signal, so lights, that tells to the train if the next track circuit is occupied or not by another train, so that the train knows if it has to stop or it can continue his travel. But in order to safely know if there is something after the signal or not, then the signal has to be close enough to the track circuit so that you cannot hide the train before the track circuit, but after the signal. Okay, so that's the property here that we will need to validate, that the signal associated to its track circuit is close enough. But what is close enough? Here we can guess that it is directly related to the length of the train. So once we have the minimal length of a train, we can compute the maximum acceptable distance and compare it to the actual distance of any switch with any signal with any track circuit. So if we have this only on paper, what do we do? So first, we need to create a database and then run the tool on it. But to create this database, we need to extract all important information from this image. And after that, check these red arrows. To do that, we can use another tool that is the ClearSeed diagram editor. It can be used to import an image and then highlight information on it. That's what we have here in yellow. And from that, we will create a database for the ClearSeed data solver. So let's do this demonstration. So for this one, we import our PDF image here, and we will create an object that we will save in a database. So for example, we start here with a track boundary. So if it is the code track 1, let's call it a track 1B for beginning. And the position is 0 as it is shown in the image. Then we can link this track beginning to the next signal, the position 80, signal 1. And we know that this signal is protecting the track circuit number 2. So we can do the next operation saying that the track circuit 2 is at the position 100. And that way we can link this object to the other and so on. Here we define in advance 3 different kinds of objects: the signal, the track circuit, and the track boundaries. But you can add any other kind of object that you want. For example, a switch, you can add beacons, and so on, depending on your need and the kind of object that you have. So here we finish to save all these information with the last track boundary here. So we had this last object, the track boundary end at the position 300, and that's it. So once we have all this line, all these dots in yellow, we have selected all of them, and we can save them in a database. This database is in a XML format or YML, and it can be also exported in different other formats. But we can read it directly with the Crescenta solver to run the rules on it. So if we go on the ETCS part, we have this rule for the computation between the distance and between the signal and the track circuit. So let's import the data. The data are here, so it's this format. And in Orange, we know how to read it with the tool. So now we save the results in this folder, and we can run the validation. So again, you have the rule running. On the top left, you have some metrics about the number of rules remaining, and so on. And on the top right, the general information. If we take a look at the results, we have these three format reports. And for the Excel one, again, we have the traceability, the import status saying it is okay to read this data, and the general results with the details for this rule when you click on it. So you have this error message saying that the signal 1 is actually too close, too far away from the track circuit. Okay, so that's how we validated this data from the paper, then to the database, then to the validation report. Okay. So if you want to find out more about data validation, formal data validation, you can take a look on the two links here below. And also, if you have any question about a project or something that you want to ask, don't hesitate to contact us on the email below. And we'll have some business trip.
Yeah, I'll be in New York City, Pittsburgh, Toronto, and Montreal in January. So don't hesitate if you want to book a meeting with us. Yeah.
Thank you.